Thank you. Thanks, Maria, for inviting me. And Maria caught me after a talk at Stanford and convinced me to come out here and talk to you all. And it didn't take much convincing because I'm really glad to meet new people who are interested in robotics and autonomous systems. So it's a pleasure to be here. I am going to talk today about a topic that I've been getting really interested in my lab and in my research, which is game theory. And of course, when I say game theory, I'm not talking about Sunday night football or basketball or anything else. I'm talking about what's usually considered in the context of economics, mathematical game theory. So my research as a whole focuses on multi-robot systems, or how do you develop algorithms for groups of robots to interact with other robots or other humans or other intelligent actors. And it turns out game theory is a very fruitful discipline to mine for developing algorithms to do just that. So I'm going to start by telling you a little bit about what we do in my lab historically, and then I'm going to focus into a few topics related to game theory that we've been working on. So my lab is called the MultiRobot Systems Lab. We're at Stanford, just down the street in the Aeronautics and Astronautics department. We work quite a bit with quadrotors. Here's a typical quadrotor. This particular one is one that we purchased and then heavily modified in the lab. So we do most of our work that we do focuses on coordination and collaboration among groups of quadrotors. So here you see 3 quadrotors performing in this kind of dynamic dance. This is using a tool that we called virtual rigid bodies. So basically these robots are figuring out how to maintain a formation with respect to one another while that formation is tumbling in space. We use the same suite of tools to enable human swarm interaction. So how does one human control a large swarm of robots? So here these robots are trying to maintain a formation while avoiding collisions and responding to the human's control input. We're also interested in perception-driven control and in cooperative situations. So here we have 3 quadrotors with downward-facing cameras, and they're holding a formation relative to one another using only knowledge of their camera images. So they're looking at features that overlap in their neighboring images and figuring out their relative pose and using that to control to a formation. We're interested in all kinds of aerial vehicles. So this is a tiny fixed-wing aerial vehicle that we modified in the lab to be autonomous. We're also interested, and this is more pertinent to today's talk, we're interested in competitive scenarios. So here we're looking at a police surveillance scenario where you have some drones which are trying to do surveillance on a suspected criminal, and the criminal can hide in these little blackout regions, which we think of as buildings or something else. And then those patrol aircraft were trying to track that suspected criminal. And then we also try to do as much work outdoors in the wild as much as we can, working with real experimental systems. So here's an example of a deployment we did in a research forest in rural Massachusetts, where we deployed 5 drones autonomously to perform coverage. And the idea was that these drones would fly up and out over this forest to take images, and those images would then be used by forest scientists to study the health of that ecosystem. So here you can see the images taken from one of the drones as it flies up and out over this area. So we're not only interested in drones, although we have a lot of in-house expertise with drones. We're interested really in any kind of autonomous system. So this could be mobile robots, could be autonomous cars, could be underwater boats or surface vessels. So here we're basically anything that groups of robots can that any application in which groups of robots can perform that application better than a single robot. This is what we're interested in. So for example, for environmental cleanup operations, oil spill cleanup and so on, we can imagine deploying a group of boats to parallelize the operation of cleaning up the oil spill. Smart agriculture, so deploying robots to go selectively water or spray pesticide or even harvest crops. Cooperative forest fire fighting or forest fire monitoring. So having a group of drones or a group of fixed-wing UAVs that can go up and figure out where the forest fire front is and even automatically drop retardant on the forest to control where the front spreads to or to extinguish the fire. So we're interested in problems in disaster relief where people might be trapped in rubble, and we want to deploy maybe ground vehicles and drones to target where survivors might be. We're interested lately in cooperative construction, and this is potentially really powerful in space construction operations. You know, launch vehicles have very limited capacity, so if we can fly up construction material in little packets and then have robots climb around a structure and build out, you know, a large space structure like this, that would potentially allow us to build very large and elaborate structures in orbit. And then one of the biggies lately for us is transportation systems. I mean, we're all experiencing the transportation revolution that's coming with autonomous vehicles. And we're specifically interested in multi-agent autonomy on the road. So how do you design an autonomous car, an autonomous planning policy that plans intelligently with respect to other vehicles so that it knows how to merge onto the freeway? It knows that if it nudges into that crowded lane, other cars will make way for it. So today I'm going to focus in on game theory and concepts from game theory and how we can leverage those concepts to develop intelligent algorithms for robots to interact with other agents, whether they're human or robotic. So I'm going to talk first about autonomous drone racing. This is not an end in itself. It's a fun prototype to develop algorithms that will be used in other scenarios, right? I mean, drone racing is cool, it's exciting, but it's not going to change the world. What's going to change the world is autonomous driving, autonomous package delivery, autonomous air taxis, and these are the technologies we're targeting. But drone racing is just such a nice application to think about as a way to study problems that are relevant in this space. So with that in mind, what is the state of human drone racing? So human drone racing is sort of in this transition phase. It's starting to become a pro sport, actually. You can watch drone racing on one of the ESPN channels. There are professional leagues. This is the FPV league, which is first-person viewer. And you can see, this video I think is pilfered shamelessly from FPV's website, so there's a photo credit. But what you can see here is the incredible feats of perception and control that are happening very quickly with very limited information and still giving reliable trajectories for the robots. Now, there's a lot of really difficult perception problems in here. That is no doubt an interesting problem for robotics. But what I'm going to talk about is a little bit different. It's a planning issue, and it's planning competitively. So what you can notice here in this drone racing scenario is that these racers are competing with their opponents. So they see the other drones in front of them, and they strategize. Do I cut on the inside to gain a positional advantage, or do I hold off and swing around on the outside because I think I have a speed advantage? If I think there's a drone behind me, can I anticipate where he's going to go and try to prevent him, block him from passing? And so the question is, how can we take these strategic insights from human behavior and turn them into an algorithm that can be used by a robot? So here's an example of what we've developed in the lab. I find this quite exciting, although admittedly you might not find this quite as exciting as the human-flown drones. So what you're looking at is two drones that are racing against one another, and you can see the trajectories that they're planning. They're these little worms that are growing out from the drones, and they're using onboard vision to detect the relative position of each drone with respect to the other one, and they're flying through gates, and they're basically executing a scaled-down version of what you saw up here. So what we've developed is basically a game-theoretic planning algorithm for these drones to compete against one another. And I'm going to explain now how that algorithm works. So we're using a strategy that's well known from game theory called iterative best response. And it's a strategy that mathematicians mostly, have been using to study Nash equilibria. So I'm not going to tell you mathematically what a Nash equilibrium is yet. I'm going to get there in a little bit. But I'm just going to say that they're very hard to compute in general. And so mathematicians want algorithms that help them compute Nash equilibria in economics, in sociology, and other fields. So one of these algorithms is called iterative best response. And it's very simple. It goes like this. I am, meaning I'm going to pretend for the sake of this discussion that I am this green drone. And so all the computation I'm about to discuss is being done on board this green drone. The gray drone is my competitor. I want to beat him, and my objective is to get farther along the track than he gets in a certain amount of time. So what do? I first assume that he's going to do what he's currently doing, like maybe I think he's just going straight at a certain speed, and I'm going to plan my optimal trajectory with regard to that hypothesis. And then I'm going to lock my trajectory in place, and I'm going to simulate what he might do in response. That's his best response. And then I'm going to lock his response in place, and I'm going to simulate what I might do in response to that. That's my best response. And I do this again and again. That's iterative best response. And if I keep doing this, and if I'm lucky, I'm going to reach a Nash equilibrium. So what's known about this algorithm? It's known if it converges to a Nash equilibrium. But it's not known whether it converges in general. There are very restrictive mathematical conditions under which we know it converges. They're almost never true in a scenario like this. So if it converges, we're good. And otherwise, we're in a bit of unknown mathematical territory. So what is mathematically a Nash equilibrium? It's sort of like mutually satisficing. It means basically that I am doing the best thing I can do to optimize my own utility or objective function, assuming that I can only act on my own. And the other guy is also doing the best thing he can do to optimize his utility function, assuming he can only act on his own. So in other words, no player can unilaterally improve their objective, and that describes a Nash equilibrium. So this is what I call a meta-algorithm. It's kind of like a philosophy to apply to design a true algorithm. So how do we actually use this philosophy to design an algorithm? In other words, what are each of these iterations that we're performing in iterative best response? So this is part of what we've studied in this domain. So let's put a little bit more mathematical structure on this. Here's our track. And we have some known center line, and we're trying to move as far along the track with respect to that center line as possible. We want to ultimately move farther along that track than our opponent. And so we phrase this as an optimization problem. It's a constrained optimization. Our objective is get as far along the track as possible, and this is a function of our own position. And then theta just denotes the entire collection of our control inputs that result in this set of positions. So when I say theta I, I mean the full policy or the full trajectory of agent I. So this is subject to a number of constraints. Dynamic constraints. I can only move so far in a certain amount of time. Collision constraints. I don't want to hit the other drone. That's game over for both of us if there's a collision. Track constraints. I want to stay on the track. If I don't, that's game over for me. The other guy wins. And input constraints. I can only muster so much force, so much thrust from my rotors. So subject to all these constraints, I want to optimize this objective function. Great. So far we're just in the territory of constrained optimization. It's a classical subject. We know how to solve this problem. What makes this a game is that this optimization, which is being performed by agent I, is coupled with the symmetric optimization that's being performed by agent J. And that coupling occurs, strangely in this case, only through the collision avoidance constraint. The only thing that prevents me from going as fast as I can straight on is the fact that you might be there in front of me and I have to avoid colliding with you. And this is a peculiar aspect from game theory. This is a special niche of game theory. So these kinds of games are called generalized games, and the equilibria that we're trying to seek are called generalized Nash equilibria. And basically, the incorporation of these constraints adds a lot of mathematical difficulty. And you might think this is exotic, but it's not. This is actually how robots who compete with one another, autonomous cars who compete with one another, this is how they interact, right? If I'm on the freeway and I want to go and the freeway's clear, I just go. The only thing that makes me do something other than that is the fact that I might collide with somebody, right? This is what makes merging hard. This is what makes traffic jams happen. So this is really fundamental to the way robots interact with one another. So skipping too much detail, suffice it to say that iterative best response for these generalized games where you have coupling through constraints, they don't work very well. They converge to solutions that tend to be highly imbalanced in the sense that one player has a huge advantage over the other. They're very unnatural kinds of Nash equilibria. So what we've developed is an algorithm that we call sensitivity-enhanced iterative best response that seeks equilibria that are more natural and that are favorable to the ego agent. So in other words, I'm the ego agent, I'm doing this computation, and I'm going to look for an equilibrium that biases towards an advantage for me. And how does this work? So essentially what we do is we think about the following high-level concept. So how can I influence my competitor? I can influence my competitor through threat of collision. So if I insert myself in the future, if I plan to move a little bit in front of my competitor, I know that if I don't move too far in front of my competitor, but I know just a little bit, that competitor is going to move out of my way. They're going to yield to me to a certain degree. The question is, how much can I push that bound? How much can I insert myself into that guy's trajectory and trust that he'll yield to me? And the way that we quantify this is through what's called a sensitivity analysis. So consider this object here. This is the, okay, a little bit technical, it's the Lagrangian at the optimal trajectory planned for the opponent at the previous iteration. So I'm planning for myself, I'm planning for him, I'm planning for myself. Suppose I've just finished planning for him. This is the value that I've found that would be optimal for him. And we'll call this L star. So this thing is a function of my own position in the sense that if I move a little bit, it's going to change his optimal value. It's going to change his L star. And how do I quantify that? I take partial derivatives of this. So I essentially expand this in a first-order Taylor expansion. Here's the first-order term, and here's the second-order term. The second-order term says, how much can I nudge him out of the way? And what is it mathematically? This is the sensitivity of J's cost with respect to I. That's the ego vehicle's trajectory. This is basically the partial derivative of the collision constraint times the Lagrange multiplier that he is using to enforce that collision constraint. The Lagrange multiplier basically says how much is he willing to avoid collision with me, and then this is that collision, and so this says, okay, how much can I move him out of the way by leveraging his Lagrange multiplier. So this is our lever to move him around. So how do we use that lever? We take this term, we put it right into our objective function, multiply a little constant so we're not pushing too hard or being too aggressive, and now we optimize this thing. So we've changed, previously we were just optimizing this guy, now we're augmenting our objective function, we're optimizing this thing. This is what we call sensitivity enhanced iterative best response. And then we put this in our iteration for the ego vehicle back and forth, subject to the constraints that I showed before. So a few things you might ask. Is this computationally reasonable? I have to solve all these optimal control problems online. How fast can I do it? Turns out pretty fast. So this is, with the effort of my grad students in my lab working to optimize this, we can do one set of iterations in 20 milliseconds. And so, depending on your time budget, if you have, say, 1 second per plan, then you can do, what is this, 50 iterations or 5? Somebody help me. 50, thank you. Okay. 50 iterations. That's a pretty slow planning update rate. So maybe if you want to plan at 10 hertz, then you can do 5 iterations. And we find in practice that's fairly competitive. Then the other question is, okay, you've just changed your objective function. What can you say about this? Are you still solving a meaningful game? And if so, what is that game? So it turns out that we can prove a theorem that says that despite the fact that we're adding this extra piece to our objective function, if you do this iterative best response and converge to a fixed point, that fixed point is still a Nash equilibrium for the original game. Even though you've changed your objective, if you look at the fixed point, it's the same. It still satisfies the conditions for a Nash equilibrium for the original game. So we're still solving the original game. We're just biasing the search towards a different Nash equilibrium. Okay, so it's about as mathematical as we're going to get in this talk. I hope I conveyed the motivation and some of the tools that we're using. So let's look again at this experiment. So you can see now these are the plans that each agent is using. You can see that they're planning over some horizon. In this case, it looks like it's about 2 or 3 seconds of a horizon. And what I didn't talk about is perception, although there's quite a bit of perception going on here. Each agent is looking with an onboard camera at the competitor, and that's independently controlling its yaw it turns out quadrotors can yaw independent of the rest of their motion, so that you can think of this like a free gimbal mechanism. So we're yawing to always be looking at our competitor with our camera, and then we're using computer vision to estimate, even though we only have a monocular camera, we're estimating the full relative 3D pose, or relative 3D position, rather, of the other drone with respect to us. And then that relative 3D position is what we use to plan against. So we say, okay, I see he's there. Now I'm going to do iterative best response, plan, 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 plan. And then here, now I'm going to execute my plan. So that's what we're doing. So you might ask a few things. Can this be scaled up? Can you do this among a lot of agents? That might be your first question. Your second question might be, can you scale it to 3 dimensions? The answer to both of those questions is yes. And the third question might be, can you prove that this game-theoretic planning strategy works better than other state-of-the-art strategies in a real-life racing game? And the answer is yes to all those questions. So here's an example of that same algorithm with some tweaks running on 4 drones. So all 4 drones are using the game-theoretic planner to race against each other. In fact, I misspoke. 2 of the drones are using a game-theoretic planner, and 2 of the other drones are using some nominal policy that's not the game-theoretic planner. And then we can also do this in 3 dimensions. So here's 6 drones. 3 are using game-theoretic planner, 3 are using some other nominal policy. And you can see the track has lots of ups and downs. What you can't see is the track also has constrictions. And we can also make the track go vertical and do spirals and really move arbitrarily in 3D space. And we can do all this in a computationally efficient way through leveraging parallel computation. So what about performance? Does this actually outperform state-of-the-art algorithms? And the answer is yeah. Actually, it dominates state-of-the-art algorithms. So these plots are a little bit hard to understand, but let me start at a high level. So the lower these whisker plots are, the better off you are. So this is basically lag from the winner. The lowest bar is the winner, and then this indicates how far number 2 was behind. This is number 3, and so on. So low is good. You can see the game-theoretic players here, there are 3 of them in this example, virtually always win places 1, 2, and 3. And the other players using a state-of-the-art model predictive control algorithm placed in the bottom 3 places. And similarly here, the game-theoretic planning always takes places 1, 2, and 3, and model predictive control takes 4, 5, and 6. So now, how do we set up the game to promote competition to really study which of these planners is better? So we do the following. It's a little complicated, but I think you'll see the sense in this. So we consider 2 variables, top speed and planning algorithm. So what we do is we let the game-theoretic planner be slower, meaning it has a lower top speed, but we seed the start positions so that they're in front. And then we let the MPC, the competing algorithm, be faster. They have a higher top speed, but they're started in the back. So you'd think that if these faster guys are smart, they can overtake these slower guys and win the race. And then we turn the tables. So we let MPC, the, say, quote-unquote dumb algorithm, be slow, but we seed it in the front of the box, and we let GTP, game-theoretic planner, be faster, but seated in the back of the box. So again, you'd think if the fast guys are smart, they're going to be able to use that advantage and win. So what do we see from these plots? Well, when we let GTP, game-theoretic planner, be slow, but start in front, they effectively block. They defend their position, and they almost always win. When we let GTP, game-theoretic planner, be fast, but start behind, they effectively leverage their speed and overtake, and they virtually win every time. So this hopefully convinces you that it makes sense to think about things in a game-theoretic perspective. So where are we taking this? We are expanding along multiple different directions. I'll tell you about one of the most exciting things we have going on. We are collaborating with Microsoft Research. There's a group there that focuses on a very high-fidelity drone simulation environment that's called AirSim. It's built on the Unreal physics engine that's used commonly in video games like Grand Theft Auto. And we're working with these guys. The leader of that group is called Ashish Kapoor. He's a good friend of mine. We're working with these guys to develop a virtual drone racing competition. And we're inviting competitors from anywhere. If you all are interested in this, I very much would be delighted if you all would field a team for our competition. So our competition is going to be, it's called Game of Drones, forgive the pun. And it's going to be featured at the NeurIPS. NeurIPS, as many of you know, I'm sure, is the premier machine learning conference. It happens every year in December. And so we're going to be running a competition track in NeurIPS this year in 2019. And essentially the way this works is we've developed 3 tracks, which range in difficulty from simple to medium to hard. And the tracks we've intentionally made interesting. So this one is a real physical building at Microsoft Research. It's called Building 99, and we're flying drones virtually through this building. And then this is a famous national park in China that's very beautiful, flying around there. And then this is just a typical suburban neighborhood. And so we're taking entries in various tiers, assuming different things about perception and planning and capabilities of the drones. And we're having a qualifying round where people can submit their code. So you can learn more about this competition here if you follow this web address. You can submit your code to get scored, and then we'll keep a leaderboard publicly available online, and the top N scorers on that leaderboard will be invited on site to the NeurIPS competition, and then we'll race head-to-head in live competitions with big video screens. So hopefully it'll be a kind of a World Cup style head-to-head. We'll have a competition bracket and so on. So we have over 60 teams already registered from all the top universities around the world, and we're really excited about this, and many companies as well. So we've extended this now to domains which are getting a little bit closer to having a real impact, I think, when it comes to applications. So we're looking at autonomous driving. We feel that game-theoretic interactions are really fundamental to autonomous driving. Every time you navigate a stop sign, every time you negotiate with a pedestrian who's crossing the street, every time you merge on the freeway in traffic, your brain is doing some kind of game-theoretic calculation. Does that mean we're solving very complex algorithms to find Nash equilibria? I really don't know. I'm not a neuroscientist, but people are very good at negotiating with other people to find Nash equilibria. So with that in mind, we have looked at extending racing to cars. So these are scale cars that we've modified to be autonomous. And it's the same general setup as the drone race, but here we're contending with the more complex dynamics of cars. So we're looking at a bicycle model with non-holonomic constraints, and we're also planning in the continuous trajectory space, not the discrete trajectory space. And we can extend all these tools more or less directly. And then we've gone to the field and we've implemented this on a full-scale autonomous car. So this is an experimental autonomous car called X1 that was developed in the lab of Chris Gerdes at Stanford, and we work quite a lot with Chris Gerdes. So the car has 2 of my grad students on board, and we are racing on a simulated racetrack against a simulated car. And you can imagine why we want to do that, because if we have 2 real race cars and we're testing experimental planning algorithms, that could be a very expensive test, right? We don't want to have collisions in real race cars. In any case, we find that whether we're blocking, that is whether we're starting behind with a higher top speed, or starting ahead with a lower top speed, or we're passing, that is we're starting behind with a higher top speed, in either case we dominate the competitor. So the green bars means that the game-theoretic planner won. You can see there's something stochastic going on here. We don't always win, but we very likely are going to win. Okay, so in the future we're looking at things like not necessarily fully competitive games, not zero-sum games. These are going to be much more relevant for the driving scenarios, right? It's not that I want to crush the other cars on the freeway, far from it. I want to navigate safely while reasonably meeting my own goals and trying to optimize my own objectives. So there's a certain degree of collaboration that we want to understand, and we're studying that now. So let's shift gears a little bit and talk about another application that is quite relevant to situations today. So a lot of people are flying their hobby drones, and some people are flying their hobby drones into airspace in airports. This has been a particular problem in the UK, where Gatwick and Heathrow airports have been shut down for hours because of silly people flying their drones in this airspace. You can see a no drone zone here, and I'm not sure which airport this is, somewhere in the UK. So people, various policing agencies in Europe mostly, have been training hawks to take down drones, which is a fantastic idea for a movie, but I don't know if this is a good idea in real life. But this is fact. They're doing this. So we thought, well, maybe we can do this a little bit better. Maybe we can develop drones to take down other drones. Nobody gets hurt. Hawks don't get hurt. So if every airport can have a small fleet of drones which can go intercept and take down a rogue drone which is flying in their airspace. So there are many other problems you can imagine where this would be interesting, but I think this airspace control example is the most pressing. So what we've developed is a quite simple geometrically inspired game-theoretic algorithm whereby multiple pursuing drones, these are the triangles, can intercept and disable multiple evading drones. Those are those circles. And the algorithm works in 3D or 2D. Here's the 3D example. And it requires very simple computation that can be performed on board drones with very lightweight computing on board. And there are strong guarantees. So we are guaranteed to capture any number of evaders in finite time. Maybe that is a very large finite time, but it'll happen eventually. And this has to happen in a finite space as well. If the space is unbounded in one area, then we have to work a little bit harder. Our algorithm still is effective there, but the proofs don't hold up quite the same. So let me describe what's going on in this algorithm. I'm going to use a 2D example because it's easier to see what I'm talking about. So the drones, these are the guys we're in control of, the pursuers. These little mean guys are the evaders that we're trying to capture. The drones compute what's called a Voronoi tessellation of this space. This can be done in 2D or 3D. This is a standard computational geometry problem that can be solved very quickly in a distributed way online. If you're interested in the computational complexity, I can talk more about that, but suffice it to say it's a solved problem. Now, any drone which shares this Voronoi facet, a Voronoi edge, with a bad guy, looks at that Voronoi edge and computes the center point. In the 2D case, it just looks at this point, takes the difference between the two, or the average between the two, and makes that its target, flies to that target. This guy flies to that target, and likewise, these guys fly to this target and this target. So you can see that this is not perfectly aligned with the rogue drone. We're not doing a pure pursuit. We're not going directly for this guy. It's kind of hedging your bets. There's a good reason for this, and I'll talk about why that is. If you don't share an edge with one of the bad guys, you can either hang out, play zone defense, so to speak, or you can choose one of the guys arbitrarily and go straight for him and do pure pursuit. What is the intuition behind this and why does it work? You can see how simple it is, and that's what I was just showing in those previous simulations. So let's zoom in on this little Voronoi cell of this bad guy. It looks like this. We have two pursuers and one evader. What we want to do, if we were to phrase this as a game, what we want to do is design these two guys' strategy to drive the area of this cell to 0 as quickly as possible, right? That's one thing you could say is a reasonable objective for a game. These guys ought to drive the area of this thing to 0 as quickly as possible. That's going to result in capture. However, this guy has something to say about that. The evader can affect his area by where he moves. So what do? We assume that the evader is going to do the worst. He's going to try to draw out that time. He's going to make that time that the area goes to 0 as big as possible. That's the max. Then subject to that, we want the pursuers to minimize. That's called a Stackelberg game, or a minimax game. So we're minimizing the worst case to capture this guy. This is what we would want to do. This is computationally intractable. This is really not something you can solve online. So what do? We take a greedy approximation. Instead of optimally finding the minimum time to capture, we instead find the rate at which we can most quickly drive the area down. So at the current time, how quickly can we make the area decrease? That's a dot, right? So the evader is trying to optimally increase a dot, and we are trying to optimally decrease a dot. We want a dot to be as small as possible. That's decreasing. And it turns out you can solve this analytically. It's really amazing. You can push right through the geometry and solve this analytically, and you find that regardless of what E does, this is another strange fact, is it's independent of the evader strategy. The pursuers want to do exactly what I said on the previous slide. So this is just written in mathematics. That is, every pursuer moves directly toward the center point of this Voronoi edge and go there as quickly as possible. And that's the policy, and that's the justification for the policy. So when you extend to 3D, instead of going to the center point of an edge, you pick the centroid, so that shared area that you share with that Voronoi cell is now like a plate. It's a facet in 2D, and you find the centroid of that plate and go towards the centroid. And so you can see again now with a little bit more intuition of what's going on under the hood, what these guys are doing. This is interesting because there's no explicit teaming going on, but there is implicit teaming happening. The robots automatically figure, okay, I'm going on this facet, and then that guy's going on this facet, and it all works out. So they implicitly self-divide into teams without having to solve some kind of integer program or assignment problem. And you can see it also leads to this kind of pack hunting mentality. They surround the pursuer and try and trap him on all sides simultaneously. So it's very simple, but it leads to pretty complex behavior. Yes?
Are you somehow modeling the uncertainty that goes with the, right now you're probably assuming that there's a godlike knowledge of the localization of the data versus the pursuer?
Yeah.
How do you incorporate just some stigma?
Yeah, absolutely. So this is, I'm going to talk about that in a few slides. Yeah, this is this is the most reasonable thing to ask. Yeah, most reasonable thing to ask. So we do have a result if there's uncertainty, absolutely. So as I said, I like to push all my algorithms into hardware and make sure that they work on real systems. And so here's an example, again, with perfect localization, there's no uncertainty here, where we have these pursuers. These are the bigger boxy robots, and then the evaders are the little guys. And to make this extra interesting, this evader is controlled by a human who was one of the authors on the paper. So he has a God-eye view of everything, and he knows exactly what everybody's policy is. So he knows what the pursuers are going to do, and he still can't evade capture. I don't know if that says something about the student or the algorithm. The student's brilliant. He got his PhD, and now he's making way more money than I'll ever make. So it's definitely the algorithm working here. But you can see he got captured. He wasn't even the last one to get captured. One of the autonomous evaders got captured last. So I like to point that out to him. What about uncertainty? And this is always going to be the case, right? We're always going to be measuring the evader with some onboard perception, and there's going to be some uncertainty involved in that. So if we assume that we're measuring the evader with something like a Kalman filter, an extended Kalman filter, we're going to have some uncertainty ellipse, which I'm displaying here as this little bubble. So maybe the true position is the red guy. Where we think he is somewhere inside this elliptical bubble. And then the relevant area that we're trying to collapse to zero is called his safe reachable set. And that is simply the set of points that he can get to in the space before any of the pursuers. And you can see that was that polygonal cell previously, but now because there's uncertainty, the geometry is more complex, and these edges become bowed. And they can become quite bowed depending on the configuration. So this is that safe reachable set in 3D, and this is the safe reachable set in 2D. So the geometry is more complex, but the algorithm's the same. Try to move to decrease that area as quickly as possible. Turns out the math is more complicated, but you can solve this computationally efficiently, and it is a very similar policy. Every pursuer finds a particular special point on this boundary and then drives towards it at full speed. And you can see what happens here. You can see the uncertainties evolving as the agents collect onboard measurements, and they're working together to collapse that safe reachable area. So what can we prove about this? Well, a couple of things. So we can prove that if that ellipse never grows, if it only shrinks, which is debatable, depends on our estimator and what we know about that other agent. But if it never grows, then we can prove that he'll never escape. That the area, the safe reachable set, will always remain bounded, right? So we can drive it down, in practice, we drive it down to a certain size and then it doesn't grow any farther. Now, what we find in practice, which we haven't been able to prove, is that if your estimator gets better the closer you get, which is reasonable, right? Your machine vision algorithm is going to get finer detail as you get closer to your target, and so likely that error ellipse is going to get smaller as a function of the range. As you get closer, your error ellipse gets smaller. Then under a certain functional relationship between the two, that is, if the area of that ellipse of uncertainty decreases fast enough as a function of your distance, then we can achieve capture. That uncertainty ellipse collapses, and then with it, that safe reachable set collapses, and we achieve capture. So this is something that we're working on still, but that's what we have as far as this robust game-theoretic pursuit evasion. So we've done this in hardware as well. We have the same setup with a human-controlled evader, which is here, and then 3 autonomous pursuers. And in this case, we are using onboard vision to estimate the position of that pursuer. And so there's uncertainty related to that onboard perception. And we still get capture in this case. I'm not showing you these corner cases, but there are cases where that uncertainty ellipse doesn't go down fast enough, and the robots collapse to some fixed configuration. They don't actually achieve capture. We call that containment. They achieve containment. And then that evader may drift around, and the pursuers will drift around with it, but he never escapes. All right. Let's move along to something that I might call kind of a dual problem to pursuit evasion, which is collision avoidance. So in pursuit evasion, we have drones trying to run into other drones to disable them. In collision avoidance, everybody's trying to avoid being run into. And this is a very fundamental problem in autonomous driving and in humans walking and robots moving among humans walking. And it's also really important for drones in a cluttered airspace, right? We don't want drones to run into each other in a cluttered airspace. Unless that drone is a rogue drone in an airport. Right? Collision avoidance is something that people do just magically well. This is phenomenal how well people avoid collisions. This is a real intersection in Addis Ababa in Ethiopia. Am I right about that? I think that's Ethiopia. Or is it Eritrea? I'm going to say Ethiopia. So apparently it's called Meskel Square. And as you can see, there either are no signals or the drivers really don't care if there are signals. There are people, there are motorcyclists, there are vans, there are tiny cars. There's never a collision. So people work it out. Somehow they figure that out. So you could imagine that this is somewhat similar to routing internet traffic, right? But in routing internet traffic, you have a router which knows a lot about where all the packets are going. So that router can have a God's eye view and say, okay, you go through here, you go here, you go here. That's not what's happening here. This is fully distributed. Every driver has some limited point of view and some uncertainty about what the other cars in its neighborhood are doing and the other pedestrians. And it acts based on that limited point of view, and still there are no collisions. So we've attempted to take these same assumptions and distill them to an algorithmic setting and develop an algorithm that has similar guarantees and similar qualitative performance. So here I'm going to shift your attention to the results of our algorithm. You can see again it's using a Voronoi tessellation and this geometric principles that were used in the previous segment of the talk. Not quite as impressive again as the human example, but you can see something in the spirit of that human example. Every car only knows about its neighboring cars, and they are able to use some very fast computational policy to navigate around one another and avoid collisions in a fully distributed way. There's no centralized planning here at all. So what's the intuition? What's going on here? You'll recognize a lot of the same principles as what were at play for the previous segment when I talked about pursuit evasion. So here's the ego vehicle. Again, we're going to consider as this is going on from his perspective. Every agent computes its own Voronoi cell. As I said, this is a well-known computational geometry problem. It's very fast and distributed. And now every agent retracts the boundary of his Voronoi cell by a certain amount. We call this a buffered Voronoi cell. And the amount by which you retract it is such that if the center of mass of this guy stays within the buffered Voronoi cell, then the full physical extent of the robot stays within the true Voronoi cell. Right? You can imagine how you could figure that out. Now, this guy has a point along a trajectory which he would like to go to if he could. If there were nobody else in the space, he would move to that point. So this is given to him by some high-level planner. Maybe this planner is given by Google Maps and says, okay, go through this intersection and blah, blah, blah. And now he has to figure out how to get to that point without hitting anybody. So simple idea, project that point to the buffered Voronoi cell and go to that point. Now notice if I go to that point in the next time step, my body is still in my Voronoi cell. And if everybody else does the same thing, meaning not literally the same thing, but following the same policy, only going to the projected point of their Voronoi cells, everybody's body is going to stay within their Voronoi cell. There can be no collision at the next time step. Okay, so we have a piece of a recursion, of a recursive proof. Now what happens? Everybody's moved a little bit. No collision happens. Now we redraw our Voronoi cells. We redraw them, the geometry has changed, and we can prove that when you redraw the Voronoi cells, no Voronoi cell is empty. Every Voronoi cell has positive area, and there's a little room to move. And then you repeat, and that sets up the recursion for the proof of collision avoidance. So there's a mathematical proof of collision avoidance here. And it goes like this, right? If every robot at the next time step stays in its current Voronoi cell for all time, there's no collision. So it's actually pretty simple principle, and that's what leads to this behavior. So there's some assumptions here. For example, the assumption is that we can move to our next waypoint without going outside our Voronoi cell. And if we have some complex dynamics and some complex constraints, as you do on real vehicles, this may not be true. And I'll talk about how we can generalize to that case in a second. So in any case, we can generalize to 3D very easily. So here's in simulation a bunch of quadrotors using this policy to avoid collision. Excuse me. Let me jump ahead. Where's my video? Well, I'm not seeing how to skip the video, so we'll just watch this again. So there's a competing algorithm out there that's called reciprocal velocity obstacles, RVO, that operates under similar assumptions. It's very commonly used in the gaming industry and in the movie industry to simulate crowds moving around, moving past each other. But RVO requires that you know the velocity of all of the agents around you. And our algorithm requires only the position of all the agents around you. They both have the same computational complexity, and they both have the same collision avoidance guarantee. It's just that ours requires less information. And you can imagine in a robotic scenario or autonomous driving scenario, it's difficult to accurately estimate the velocity of your neighbor, not so difficult to accurately estimate the position of your neighbor. And so this is benchmarking in test cases against RVO, which is the state-of-the-art algorithm, that's on the bottom, and our algorithm, which is on the top. So you see, in some cases we're a little slower, in some cases we're a little faster, but in all cases we avoid collisions and we require less information. Okay, so what about more complex geometries, more complex dynamics? Well, we've managed to generalize this to the case of cars and the geometry of cars. And this requires a different kind of geometric tessellation, which we'll call, what do we call it, actually? Okay, we'll call it a generalized Voronoi cell. I'm not going to go through the details. In spirit, it's very similar. So you basically find some facets which represent the kind of collision boundaries. If every car stays within these facets, then you're guaranteed to have no collision at the next time step. And you can efficiently compute these things based on the geometry of the situation. It's a little interesting to note that this is not actually a tessellation, because if you put all of these cells together, there are gaps in the environment. So there are pieces that are not included in the tessellation. It's really just a curiosity. What's important is that as long as every car stays in its cell, there's going to be no collision. And then you set up this same kind of recursive argument, and you have a collision avoidance. So that's how you deal with more complex geometry. How do you deal with dynamics? So the way we deal with dynamics, cars obviously are dynamic objects, right? But firstly, they have a dynamic constraint, which is called a non-holonomic constraint. You can't move your car instantaneously to the left unless you're moving forward, and then you have to kind of swerve to the left. And they also have mass. They can't move immediately, change their velocity immediately. They have to do that through an acceleration. So what we do is we just map the concept, the same concept, into the input space That is the space of steering inputs and acceleration and brake inputs. So this is another geometric space. And we take this kind of safe space that we computed before. That corresponds to a set of safe inputs. And we essentially do the same projection trick onto the space of safe inputs. So you might wonder now, do all the guarantees hold? In particular, are you always guaranteed to have a non-empty set of safe inputs? And the answer is, long story short, under some assumptions about the dynamics, yes, you're guaranteed to always have a non-empty set of safe inputs. And this relies on a particular property of the dynamics that we call strong controllability. It's not true for any dynamical system. It's true for a particular class, which we call strongly controllable. It turns out that the standard vehicle model, which is a second-order bicycle model with non-holonomic constraints, does have this property, which is really, that's the heavy hitter, right? Maybe we can't control any arbitrary dynamical system, but the one we really care about is cars. And that one we can control in this way to avoid collisions. So here's some preliminary simulations. These aren't the most beautiful simulations. I would show you something a lot more high fidelity if I could, but here's at least gets the point across. We have these safe cells are shown with the colors here, and what you're seeing here is one car using MPC, that's the red car, that's the baseline algorithm that virtually all autonomous driving policies on the road and off the road today use MPC or some variant of that to plan their trajectories. So this is MPC, and this is our vehicle, which is using this MPC plus this projection technique to project repeatedly into this safe set. And so you see that we avoid collision regardless of the fact that there was a potential near collision there. And then here is a human. So here the human is being controlled by a joystick here, and the human is just kind of being a bad driver, just doing, swerving between lanes. And here's the guy that's using our buffered input cell technique. And you can see that even when the human tries to cut him off, we're still slowing down safely to avoid a collision. So, simple question, what do we do when we have perceptual uncertainty? This is obviously going to be the case in practice. Well, we can translate all of this geometric intuition into a probabilistic setting. And we can generate basically what are probabilistic buffered Voronoi cells. So same geometry, but instead of having a hard line that says if I stay here, there will be no collision, instead I have level sets of risk. So you see these numbers attached to these level sets. You can see that the geometry here is like a soft version of that hard partition. So these correspond to how much risk you can tolerate. If I stay within this level set, my risk of collision is 0.99. And that's actually a very, very conservative lower bound on the risk. Lower bound, yes. The probability of collision is much lower. It's an upper bound, excuse me. It's a very conservative upper bound. So in other words, if I stay in this level set, the probability of collision is way less than 0.99, but it's no greater than 0.99. So how this works is not, I think, not super important. We use a particle filter representation of uncertainty, which is very flexible because it is appropriate for non-Gaussian and non-linear dynamical systems. And each of these particles we consider a hypothetical location for that vehicle. And the weight of the particle tells us the probability with which we believe the vehicle to be there. And so every one of these samples carries with it a discrete Voronoi boundary. And we apply that boundary with a certain probability, which is attached to the probability of that point being the true location of the vehicle. And then we use a test, right? We say, if I go to this position, how many of these Voronoi cell boundaries will I be violating? Okay, I'll be violating 3 of them, and the probability of all those 3 violations amounts to 0.01, and so great, that means I have 99% likelihood of no collision. So we can actually formalize this and show that this is an upper bound on the collision risk, but you can see how that works. So here is that same algorithm. And I unfortunately can't seem to figure out how to skip in the video, but that's okay, it's coming up very shortly. Here it is. So you can see these cars are using this Voronoi technique with this sampling-based approach to avoid collision. And we've done this with the same scale RC cars that I showed you before. Now, one car here was estimating the position of the other using a LiDAR unit, a Hokuyo LiDAR unit on board, and taking into account the uncertainty with that estimate and so on to change lanes safely. Okay, that sums it up for my talk. So I spoke about autonomous drone racing, multi-robot pursuit evasion, distributed collision avoidance. I think these are all really important problems in a range of domains for autonomous driving and for autonomous drone delivery and various other things. So I hope you enjoyed the talk. I'd like to give some thanks to my very, very talented grad student collaborators who have really been the mental engines behind this work. These are some previous grad students who are now postdocs, becoming fabulously wealthy and famous, spreading their wings on their own. And then these are some postdocs that I worked with as well in doing this work. And these are my generous funders. So thanks to all of them, and thank you very much to you for all of your attention. I'm happy to take any questions.